This is Lab 3, the magnetic field of permanent dipole magnets. The goals of this lab were to measure the distance dependence of the magnetic field due to a bar magnet, calculate the magnetic dipole moment mu, visualize magnetic field on and off the axes of the magnet using glow script, and compare the net magnetic field from the model to the experimental B net for the 45-degree axes. Main concepts used: a bar magnet is a magnetic dipole, the Earth acts like a bar magnet, and the magnitude of the magnetic field decreases as distance from the bar magnet increases. The distance dependence n equals -2.52 and magnetic dipole moment mu equals 6.84 were calculated from experimental data. The measurements were made with the Teslameter app, and the approximate location of the magnetometer in the phone was determined and marked with rubber bands. Magnetic north was compensated for by zeroing the x-component reading and securing the ruler on a wooden table perpendicular to the length of the phone at this position, as shown below. The bar magnet was leveled on the ruler at 0 centimeters using a napkin. Observations. Number 1, when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. Number 2, as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. And the experimental data is shown to the right. The distance dependence is represented by this equation, from which we derive an equation that can be plotted to yield a slope equal to n and a y-intercept equal to ln of k. So this is the plot using the experimental data. N, the slope, was found to be -2.5246, and k was found by finding the exponent of the y-intercept. To calculate mu, I set the first equation equal to the magnetic field equation for a dipole on the axis. So at intercept ln of k, ln r should equal 0, so I used r equals 1 when I set the two equations equal to each other. And in the end, I found that mu was equal to 6.841 based on my experimental data. So this is the function I used to create the computational model. The two inputs are the magnetic dipole moment from experimental results and the distance of the observation location from the magnet. And the value of this function is equal to the magnetic field vector. And you can see the equation I used in the function and then the function below that. So this is the visual model. The observation locations are shown: 2 on axes with the magnet, represented as the orange arrows, 4 perpendicular to the axes, shown in blue, and 1 on the 45-degree axis, shown in green. All of the observation locations are at a distance of 0.1935 meters, except for the 45-degree axis location, which is d equals 0.1935 times square root of 2. And all of them have a scale factor for B of 550. For the off-axis results, the magnetic field along the 45-degree axis of the magnet was measured experimentally, and the third trial's data was compared to the computational model. You can see the experimental setup on the right and the results on the bottom. So I had a calculated B net from the experiment and from the model, and assuming that the model was more correct, the experimental data for this one had a 4.5% error. If I hadn't corrected for magnetic north, the Earth's magnetic field would act as an external field at the observation locations, and the true magnetic field of the bar magnet would not be measurable. By orienting the magnet's axis orthogonal to the Earth's field, we can eliminate that external magnetic field since mu dot r hat equals 0. If I had stuck 2 identical bar magnets together end to end and run the experiment again, the measurements for the magnetic field would be twice as large, assuming that the dipole moments of the magnets are oriented in the same direction. So in conclusion, a visual and computational model was created to represent the magnetic field vector of the bar magnet at locations on and off axes. The total magnetic field on the 45-degree axis was found to have a percent error of 4.5% when compared to the value predicted by the computational model. In the main conclusions, we can correct for the Earth's magnetic field in order to measure and characterize magnetic fields of smaller objects. And as the distance between a bar magnet and the observation location increases, the magnitude of the magnetic field decreases.